Okay, well, this seminar and the next several are all about graphs, or graphs if you like, and the equations that go with them. And lots of people have talked to me in the Maths Learning Centre from various different year levels. There are people in first year, there are people in second year engineering maths. There are lots of people who talk to me saying that they have trouble being able to tell from an equation what a graph ought to look like, and have trouble being able to tell from a graph what its equation might be. And yet they're expected to do that by their lecturers all the time. And so that's what this seminar and the next several are about. But before I get to that, I need to talk about what a graph is and what an equation is for. So fundamentally, a graph is a collection of points. Okay, so here we are in two-dimensional space, two-dimensional plane here, and every point has a set of coordinates. So this point A is just past 4 on the x-axis and just under 2, just past 2 on the y-axis. It's actually about, what is it, about 5 on the x-axis and 2 and a little bit on the y-axis. That means it has coordinates 5, 2. And so we talk about the x-coordinate and the y-coordinate. What it lines up with on the two axes is what its coordinates are. So a pair of numbers, one on the x-axis and one on the y-axis, tell you the coordinates of a point. And the coordinates of that point, if I use those numbers and sub them into some sort of equation, it may or may not satisfy the equation. So I have an equation here on the screen. It's x plus y is equal to 4. And so the purpose of that equation at the most fundamental level is just to tell me whether a point is on the line or not. So my point A here, it's got coordinates of 5-ish and 2-ish. So if I go 5 plus 2, it doesn't come out to 4. And so the point A is not on whatever is not described by that equation. So if I move the point a bit to some other spot, it will have new coordinates, and those new coordinates may or may not satisfy the equation. And I might move it to another spot and they may or may not satisfy the equation. And when I collect together all of the points that satisfy the equation, that is the graph of the equation. Okay, so that's what a graph is. I collect together all of the points who, when I put their coordinates in, it comes up to make the equation true. So at the moment, the equation isn't true. So this point here called A is going to be blue when it doesn't satisfy the equation, and it's going to turn red when it does. So I'm going to move it around and see what happens. Oh, just a second. So none of these blue points satisfy the equation, but that red one just there, it did satisfy the equation. So I've found one of the points that satisfies the equation. Oh, there's some more. Oh, interesting. Let's see, none of those seem to. Well, it looks like the points that do satisfy that equation all form a straight line. Interesting. And that's the idea of an equation. Okay, the graph of an equation is the collection of all of the points that do satisfy it. And I could do this forever and still not be 100% sure what all of the points were that satisfied the equation. But I'm pretty sure that it must form a straight line, and that all the points that are off that straight line aren't part of the graph, and all the points that are part of the straight line are part of the graph. Okay. So I could put any old equation in here and see what I get. X squared minus y equals 3 times x plus y cubed, something ridiculous. So let's start again. Oops, today, sorry. Let's see. Oh, there's some. Oh, there's another one. And another one. Oh, it looks like there's a little curve that's part of my graph just there. You can see that it is technically possible to find it this way, but it's not at all easy. I presume it's some sort of curve. It looks like my curve comes around here, but I don't know what else it's doing everywhere else. I've lost my point A. There it is. Interesting. Some sort of oval shape at the moment. Doesn't seem to have anything down here below the x-axis. Right, and that takes a lot of effort. It takes a lot of effort to find out this way by testing all lots of points. Even though my computer's doing all the work for me and I'm just colouring in basically, it's taking a lot of effort for me to try and find what this graph looks like by testing all the points. Now the way that computer graphing software normally works is it basically does that. Okay, it basically just colours in, you know, goes down the pixels and just colours in all of the things that belong, that satisfy and ones that, and leaves blank all the ones that don't. But that is fundamentally what the equation of a graph, what the graph of an equation is. Right, I'm going to draw on the document camera now. So I'm going to write that down on my notes. The graph of an equation is a set of all the points whose coordinates satisfy the equation. That's what a graph is. Okay, what that means is that the equation gives you a rule for telling whether a point is part of the graph, part of the set or not. Okay? So the equation is a rule out of the set or not. So for example, here's the point 5, 2 on the graph of 4x minus 2y equals 16. We can answer that question. So this is an equation, it has a graph, and the equation is a rule for telling whether a point is on it. I'll substitute it in. So let's see, x equals 5 and y equals 2 for that point. So we have 4x will be 4 times 5 minus 2 times 2. So I put the answer for x and the answer for y in, and that's come out to 20 minus 4, which is 16. And that's the answer it was supposed to come out to if it was on the graph. So yes, 5, 2 is on the graph. Ta-da! Okay, and that's pretty much all there is to it. And if the answer had come out to be not 16, then the point wouldn't be on the graph. And that seems very uninspiring, right? It's not particularly inspiring. You go, okay, sure. The key and the biggest idea in pretty much the entire of mathematics at school is that the equation tells you more than just that. Okay? So at the fundamental level, an equation is just telling you what points are on, how to figure out if a point is on the graph or is not on the graph if you have a point. But there's more than that. Through a long period of history, we have discovered that certain kinds of equations always give certain kinds of graphs. And that information in the algebra of the way the equation is written will tell you information about the shape of the graph. Okay, but there's more. Sometimes you can tell the shape of the graph just by looking at the equation, because some equations only produce a certain kind of graph. Okay? And more than that, sometimes if you write the equation in a certain way, it won't just tell you the general shape of the graph, it'll tell you information about parts of the graph. Okay, that is the big idea of geometry and algebra at school and basically everywhere. This is one of the biggest ideas in maths, is that even though an equation only tells you, really at the fundamental level, a rule for telling if a point is on the graph or not, because of our centuries of experience with equations and graphs, we can just look at a certain kind of equation and go, well, that must be a line, that one must be a circle, that one must be a parabola. And even better than that, if we arrange the algebra in a certain way, it will tell me information. So, oh, if I write it this way, that tells me the vertex of the parabola. If I write it this way, that tells me the centre of the circle. If I write it this way, that tells me the slope of the line. So without having to test all these points like I did on the computer screen and colour them all in depending on whether they were on or off, I can go straight to drawing it because I know what bits of the algebra correspond to what bits of the graph. And that is what this seminar, and I think I'll just do the next two on that too, because it's such a big idea. So, I'm going to start with the different kinds of graph, starting with the most common and working my way up to the crazier ones. And I will do logs and I'll do exponentials, but I'm going to start with lines. Okay. So first I'll start with lines. So it turns out, based on years of experience, from centuries of experience from our forefathers, that any equation that looks like any of these things must be a straight line. Now, these are all examples of straight lines. So these equations are rules for telling whether a point is on the graph or not. And it turns out that if you colour in all the points that are on the line and colour red and all the points that are off the line blue, then all the red points will form a straight line. Okay? They all have straight line graphs. So we're going to ask ourselves, what do these have in common? Okay, so what they don't have in common is the x's and the y's being on the same side of, being on opposite or the same side of the equation. It's possible to have the x's on opposite sides. It's possible to have the x on the left and the y on the right. It's possible to have the y on the right and the x on the left. It's possible to have them both on the same side. It's possible to just have x and not have any y's at all. Okay, so that's not what they have in common. What they do have in common is that they don't have any powers. Okay, there's no y squared, there's no x cubed, there's no root x. They're just plain x's and y's that are multiplied by plain numbers or just standing on their own, and there's possibly some plain numbers there as well. If you have an equation that looks like that, it must be a straight line. Not looks like those, but looks like having some multiple of x, possibly no x's at all, some multiple of y, possibly no y's at all, and some constant, possibly no constant at all. They are all straight lines. So the rule is, let me get my rule is, some number times x, some number times y, some plain numbers, or possibly none of those. Is the graph of a straight line. Okay, and the reason, and what they do is they call them linear equations because they are the graphs of straight lines. Okay, that's great. So now we can tell if we see an equation written down that's got some x's and some y's in it. If we see an x times a y, not linear. If we see a y squared, not linear. If we don't see any y's at all, it could be linear. If it's just got that's fine. But if all we see is multiple, some number times x, some number times y, and some plain number, it doesn't matter what order they're in, as long as they're not divided, and they're all just sitting there plainly, all pluses or minuses together, that's a linear equation. And it represents, if we colour in all the points that satisfy it, you'll get a straight line. Right. So, great. So that was the first thing I said, that the kind of graph, what the equation looks like will tell you what the graph looks like. We now know that if we see a particular kind of equation, it'll have to be a line. Great. Don't know what any of the other equations look like, but we know they're not lines. So we see some sort of equation, it has to be a line. My question next is, well, is there a way of writing that equation in a particular way that tells me more about what the line looks like? And there is. There are two main ways of writing equations of lines that give you useful information about the line. Okay? And so we're going to have to split it into different categories so that we know what our lines look like. Okay. Yes. So if you can rearrange your equation to look like this, it's called standard form. Standard form looks like something x plus something y equals something. Now the a and the b and the c are numbers, I just don't know what they are today, and they're allowed to be negative and they're allowed to be 0. The only thing you're not allowed to have is 0 equals 0 because that's just that doesn't tell you anything about x and y. So for example, 3x plus 5y equals 7. It's a perfectly good line, okay? Because the a is 3, the b is 5, and the c is 7. Or just x minus 2y equals 6. The a is 1, because it's 1x. The b is minus 2, the c is 6. I could just have, 4x equals 8. That's perfectly fine. You're allowed to have 0y. These are all in standard form, and they don't have to be whole numbers either. That's just when most people think of numbers, they think of whole numbers. I could just as easily have a half of x minus 5/3 of y equals 6. All right, that would be fine too. Okay, that's the standard form, and they could also be wacky decimals, and that would be fine as well. These are all lines that are in standard form. And what the standard form tells me is that it really is a line. If I can rearrange my equation to look like that, it must definitely be a line, even if I wasn't sure to begin with. Okay, that is basically the purpose of standard form. But one of the reasons to have standard form in the form that it is that it does help me to figure out how to draw the line. So this is where we start getting into how do we extract information from the equation to help us to draw the graph. Okay, so I'm just going to do an example. Two x minus 6y equals 24. That is an equation. I'm going to draw the graph. Now I know it's a line, so technically draw the graph of this equation. So technically that equation isn't a line all by itself, it's just an equation. But you'll find that people say the line 2x minus 6y equals 24 because for hundreds of years that has been connected with lines, so we get used to calling it a line even though it's technically just an equation. It creates a line. So how are we going to draw the graph of that equation? This is the reasoning that goes on. I know it's a line. Lines, it's a straight line. In order to draw a straight line, I just need 2 points because then I can connect them up with my ruler and then it must be a straight line. And so I only need to find 2 points on that line in order to draw it. They can be any 2 points. For the ease of my hand being able to draw it properly, I'd prefer those 2 points to be nice and far apart so it's easier to draw. But theoretically, they could be very close together, and as long as my ruler was accurate enough, I'd be able to draw my line. But hopefully, I would be trying to I could draw 2 points that are quite far apart and that would do the trick. So how am I going to find points that are on the line? This is a major issue with equations because an equation doesn't tell you what the points on the line are. An equation says if someone gives you a point, says here is the point, is it on the line? You can go, well, let's see, we'll put the x in and the y in, it comes to 24, yes, it's on the line, or it doesn't come to 24, it's not on the line. But it doesn't tell me what any of the points on the line actually are. Well, we can make it tell me what at least 2 of the points are. Okay? So let's just draw a picture. So it's a line, it's somewhere, it might be here, it might be there, it might be whatever. But one of the things that it will do is if it's not just x equals 5 or y equals minus 7, it's going to cross both of those axes. So if I can figure out where it crosses the x-axis and where it crosses the y-axis, I will be able to draw the line. Now, here's the thing. The x-axis has a 0, 1, 2, minus 1, minus 2. So this point here on the x-axis has coordinates 0, 0. And this point here has coordinates 1, 0 because it lines up with 0 on the y-axis. And this point here has coordinates 2, 0, and this point here has coordinates 1.5, 0, and this point here has coordinates minus 1.5, 0, and this point here has coordinates maybe 7, 0. All the points on the x-axis have their y-coordinates equal to 0. That's a really useful piece of information. I know that if a point is on the x-axis, its y-coordinate is 0. If it's on the x-axis, its y-coordinate must be 0 because it lines up with 0 on the y-axis. And that means that if I have a point that is on the x-axis, then y must be 0. So I could put y equals 0 into the equation and it would tell me what x would have to be to make the y come out to 0. So we had 2x minus 6y was equal to 24. So that means that 2x minus 6 times 0 equals 24. And let's see, it's not really there then. 2x is 24, so x must be 12. Because 24 divided by 2 is 12. So that's telling me what the x, this is called the x-intercept. That is the name of the place where it crosses the x-axis. So on my graph, I'm not going to have enough space to draw that. I'll make my graph bigger in a second. By the same reasoning, if the point's on the y-axis, its x-coordinate must be 0. Because look, this point is 0, 1, this point is 0, 2, this is 0, 0, 0, minus 1, 0, minus 2, 0, minus 6, 0, 1.5. All of them have an x-coordinate of 0, and so therefore, if I want a point on the y-axis, I sub in x equals 0. So let's look at my equation. It was 2x minus 6y equals 24. And when x is 0, I can just cover that up. So I often don't write the actual x equals 0 in there. I just cover that up and think, well, that's okay. So divide both sides by minus 6, which will give me minus 4. So that's my y-intercept. Okay. So that means that my graph crosses here at 12 because it was a point on the x-axis with x-coordinate 12, and it crosses here at minus 4 because it was a point on the y-axis with y-coordinate minus 4, and all I need to do is connect them up, and that will tell me what the line is. I don't need any other points because I only need 2 points to make a line. So that's lines in standard form. Okay? I should just say, I'll just do one more example shortly, quickly. Let's draw the graph of x equals 6. All right, well, let's see. X equals 6. Well, this is different. X equals 6 doesn't have a y, so I'm not going to be able to figure out a y-intercept. So since it's not possible to figure out a y-intercept, that means that this line doesn't even cross the y-axis. But there's a different way of thinking about it that allows you to find the points on the line, that allows you to draw the line. If x equals 6, then that means that it's made of points whose x-coordinates are 6. So I can't start it with so. That's not good grammar. All points on the line have x-coordinate 6. There's 6, 0, 6, 1, 6, 2, 6, 3, 6, minus 1, 6, minus 1.7. All right, they all have x-coordinate 6. And so therefore, here's 6, 0, 6, 1, 6, 2. It's a vertical line. Because if you just colour in all the points that have x-coordinate 6, you will get a vertical line. And in a similar way, y equals minus 2 will be a horizontal line. Because y equals minus 2 is telling you that the points on that line, a point will only be on that line if its y-coordinate is minus 2. And I collect together all the points with y-coordinate minus 2, and there it is. So that's lines in standard form. Okay, there's your form that has both an x and a y in it, and that the easiest way to draw that is to find its x and y intercept. And there's a point that has lines that are vertical or horizontal, and we can draw them if they look like that. There is another version of the equation of a line, which is very common as well. So I said at the beginning that you can rewrite equations to tell you information about the graph. So our standard form, I still had to do a little bit of work to get from that the two intercepts. Okay, when it was x equals a, that told me precisely everything about the line, x equals 6. But when it was 2x minus 3y equals whatever, I had to do some work to figure out where the line was and to figure out information about the line. Well, there are some ways of writing equations that you can tell the information without doing any work once the equation is in that format, and this is one of them. Most people write it with an M and a C. You may see it with an A and a B or an M and a K. It doesn't really matter what the letters are. And I would recommend, if you were actually talking to a mathematician, to not ask what is M, because they might not know what M is. So if you are able to rewrite your equation in that format, then this is called the slope or the gradient. And this is called this is the y-intercept. So we were able to figure out the y-intercept from the standard form, which told us, and we had to do a little bit of work to do that. But in this format, the y-intercept is right there. You don't have to do any work, it's there on the page. Okay? So I should just remind you what slope or gradient means. If a line goes across some number, just a second. The slope or the gradient tells you how far up or down it goes for every one across. Okay, so the fact that that's a slope or gradient, if m is positive, then that's telling me that if I go 1 across, it will go up m. That's what it means to have a slope of m. Okay, for every 1 across it goes up, that's a 1. For every 1 across it goes up m. That's what it means to have that slope. Okay, for every 2 across it will go up 2m. For every 3 across it will go up 3m. So you can figure out the slope and work backwards. So I'm going to show you both of them. Draw the graph of y equals 3x minus 6. Now I'm not going to do all the things that you would traditionally be asked to do in a school setting. I'm just going to find the bits that are mentioned here. Okay, so to draw a line, you just need 2 points. Okay, I actually have one of the points. I know that this number on the end is the y-intercept. If I write my equation in this format, that must be the y-intercept, so I have one of the points on my line already. So okay, the y-intercept is minus 6. The reason it's the y-intercept is because you know that the y-intercept is one of the points on the y-axis, and all the points on the y-axis have x equals 0. So if I put x equals 0 into the formula, I get y equals minus 6. That's why, that is the reason that it is the y-intercept. But you don't have to go through all that reasoning. You can just look at it and go, that's the y-intercept. And the slope is 3. So I know that 1, 2, 3, 4, 5, 6, that's the y-intercept there at minus 6. And the slope is 3, which means that for every 1 across, it goes up 3. So if I go across 1, 2, it goes through there. Because for every 1 across, it goes up 3, because that's what the slope means. So I can just connect those 2 points together, and that is my line. Once you've got 2 points, you can draw a line. Let's just be honest. If I went across another 1, it would go up another 3, and it would actually cross the x-axis at 2. But that's not what I'm aiming to achieve here. I just want to have a picture of where the line is. Draw the graph of y equals minus 2/3 of x. Okay, so let's look at this graph. Y equals minus 2/3 of x. There is no plane number. It's not anywhere. That means that it's 0. The y-intercept is 0. And the slope is minus 2/3. So when I said that for every 1 across it goes up m, if m was negative, that means that every 1 across it would go down m. Okay? So down if m is negative. And so that means for every 1 across it goes down 2/3. But that means that for every 2 across it goes down 4/3, and for every 3 across it goes down 6/3, and so on. That means actually the easiest way to interpret a slope that's written as a fraction is to say that for every 3 across it goes down 2. The bottom is how far across it goes, and the top is how far up or down it goes. Okay, so if you see it written as a fraction, that means that for every 3 across, it goes down 2. So some people call this the rise and this the run, if you like. That's what some people call it, rise over run. You always include, if there is a minus, you always include it in the top of the fraction. It will work perfectly well if you include it in the bottom of the fraction. It's just harder to understand. So now I can draw my graph. The y-intercept is 0. It crosses the y-axis at the spot where y is 0. And for every 3 across it goes down 2. So it passes through that point. So that's how to draw lines of certain slopes. if you have it in slope-intercept form. Now you can think about this. If someone told you that you had a line and they told you any point on the line and the slope, you wouldn't need the y-intercept because you could just draw the line. But I'm talking about how equations relate to graphs today, so I'm not going to talk about that right now. So my last example in the straight lines is going to be, here is a line, what is its equation? It's not drawn to scale. It passes through -2 on the x-axis, on the y-axis, and 5 on the x-axis. Now, there are many ways to find the equation of a line. I'm specifically thinking about the y and slope and intercept form. So the y-intercept is -2 according to the graph. It crosses the y-axis at -2. And the slope is rise over run. Okay? So let's see. It goes across 5 and up 2. So if you look at this, it went across 5 and up 2. So up 2 for every 5 across. It's 2/5 is the slope. And so that means the equation is slope x intercept. So you see the connection here. This equation is so popular for straight lines because I can usually tell just by looking at where it crosses the axes exactly what the equation is. I should just tell you a useful piece of information which not a lot of people know that I think is kind of cool. Alternatively, there is a way of directly writing down the standard form if you have the x-intercept and the y-intercept. The standard form can be written this way. X over the x-intercept plus y over the y-intercept equals 1. Always 1. That is an alternative version of the equation of the line. So that is a linear equation. It's a fifth of x minus a half of y equals 1. Very interesting, that version of the equation of a line. That is another way to find the equation of a line from the x-intercept and the y-intercept. So if you're ever in that situation and you happen to remember this, sweet. Okay, so it's actually, x over x-intercept plus y over y-intercept equals 1. That'll always work. So that's an alternative way of dealing with equations in standard form. If you just divide everything by the number that's over there, it will tell you the x-intercept and the y-intercept. Very cool. Okay. I've only got about 5 minutes left, and I've only talked about straight lines today, but I decided about 10 minutes in that that was the best plan, because there are a lot of people who need to know about straight lines. There is one final thing about straight lines I want to say, and I've forgotten what it is. Well, let me just see if we can recap where we've been first. The equation of anything is just a way of is originally a way of telling whether a point is on or off the line. Now I remember what I was going to say. Whether a point is on or off the line. But we know that if we write the equation in a certain way, we can tell that it is a line, and if we write the equation in a certain way, we can tell the different parts that the line has, where it crosses the x-axis, where it crosses the y-axis, what its slope is. I do want to, in the last couple of minutes, figure out, if I just had two random points on a line, how do I figure out what its equation is? Okay? So this equation is finding, this example is finding the equation of a line from two more or less random points on the line. Okay? So the example goes, find the equation of the line that passes through 1, 6 and 2 minus 7. Okay, it's just two random points. 1, 6 is about here. Sorry, 1, 6. 1, 6. I'm trying not to draw the y-axis and the x-axis in because I don't know where they are. 1, 6 is maybe up here, and 2 minus 7 is down here, and it passes through those 2 points. I want to find the equation of that line. What that means is I need an equation that all the points on the line satisfy. So there are many ways to attempt to find the equation of the line, and even if you don't have a way of doing it, you can always find it out. Because all you need is to think of an equation that both of those points satisfy. So let's see. Let's see. Well, the equation would have to be in one of the formats that equations come in. And so one way of doing this, so one approach, would be to say, well, the equation is y equals mx plus c for some m and some c. I don't know what the m and the c are, but that's my goal. If I can figure them out, that's the equation of the line. So I could just sub in the points and see what I get. That's going to be quite complicated, but I could do that. All right, and I know, and the m is the slope. So I could just say, all right, 6 equals m times 1 plus c, minus 7 equals m times 2 plus c, and try and figure out what m and c would have to be to make that work. But I can be a bit cleverer than that. M is the slope, okay? And I also know that m is the rise over the run. So if I can figure out how far it is between these points, I can do it. Let's see, it's 1 here, and it's 13 there. And the quickest way to do that is actually to subtract the two numbers. 2 minus 1 is 1, and minus 7 minus 6 is minus 13. So let's see, from here to here it goes the y-coordinate of the second one minus the y-coordinate of the first one over the y-coordinate of the second one minus the y-coordinate of the first one. Doesn't matter if you do it the other way around, it'll work fine. Or you can just draw a diagram. And this does totally come out to 13 over 1, which is 13. So now we know that y is 13. We can say, so actually the equation is y equals 13, minus 13. Y is minus 13x plus c. And we still don't know what c is, but at least we've figured out what m is. And now we have to figure out what C is. It's the y-intercept. If we were very clever, we could try and figure out exactly where it crossed the y-axis. It's going to be, up there somewhere. But we don't have to draw a picture to figure out what C is. We know that every point that's on the line has to satisfy the equation. So 1, 6 is on the line. So therefore, when I sub it in, the equation will be true. So the y is 6 and the x is 1. Now let's analyse this. We've got a c with plus minus 13, so really we've subtracted the 13. If we add 13 to both sides, it'll make it go away. That's the full working. So minus 13 plus 13 is 0, and 6 plus 13 is 19. And so the c is really 19, so the equation is minus 13x plus 19. Remember, the goal was not to get a number. The goal was to get an equation, which I have. I have an equation, and all of the points on my line satisfy it. It's probably worthwhile subbing in the 2 and the minus 7 just to make sure it works. Minus 13 times minus 7. It's not going to work. No, sorry, subbing in the 2. The x is 2. Minus 13 times 2 would be minus 26. Minus 26 plus 19. Well, minus 26 plus 20 would be minus 6. So plus 19 would only give you minus 7, which is what the y is supposed to be. So it does work. It works for both the points on the line, so it will have to work for all the points on the line. So that is a way to find the equation of a line that joins 2 points. There are other ways. Those people getting antsy, but I will just do alternatively. An alternative method is to imagine that we have a random point in the middle. Not exactly in the middle, it doesn't have to be in the middle either. We imagine we have a random point, and we know that whatever the point is, like it could be any point on the line, but whatever the point is, the slope is the same on the line all the way along the whole line. So if I figure out the slope from here to here, it'll be the same as the slope from here to here. The same as the slope from xy to minus 2, 7. So if I do the slope from 1, 6 to 2, 7, we know that that's the same as, it's plus 2 minus 7, isn't it? 1, 6 to plus 2 minus 7 was minus 7 minus 6 over 2 minus 1. Maybe I should do the 2 and the 1. No, that's okay. And on the other side, I could do, it doesn't have to go from here to here, it could go from here to here, it doesn't matter. So I'm going to go y minus 7 over x minus 2. That's the slope between these 2 points, that's the slope between these 2 points, and that is the slope. So I get minus 13 over 1. And so if I multiply both sides by x minus 2, I will get and if I subtract 7 from both sides, and that is an equation of my line. So that is another way. And there are other ways as well. But these are the two most common ways of finding the equation of a line that joins 2 points. And that will do for today.